What if I told you that most A/B tests are leaving money on the table? While companies run thousands of A/B tests, they're often missing crucial insights that could 10x their impact. The secret? Combining the rigor of A/B testing with the power of machine learning. Traditional A/B testing tells you what happened. Version B increased conversions by 15%, but machine learning can tell you why it happened, who it worked best for, and when to apply these insights to maximize results. Today, we're diving into A/B testing with machine learning, a game-changing approach that's revolutionizing how data-driven companies make decisions. We'll explore how ML enhances every stage of A/B testing, from smarter experiment design and real-time optimization to sophisticated analysis that uncover hidden patterns. By the end, you'll understand how to build ML-powered testing frameworks that deliver deeper insights and better business outcomes. Let's start with why traditional A/B testing isn't enough. Traditional A/B testing follows a simple formula: split traffic randomly, measure a primary metric, and declare a winner. But this approach has fundamental limitations. First, one-size-fits-all results. You get an average effect that might not apply to different user segments. A feature that increases conversions for mobile users might decrease them for desktop users. Second, limited insights. You know version B won, but you don't know why. Was it the color, the copy, the placement, or something else entirely? Third, static optimization. Once you pick a winner, you're stuck with it, but user behavior changes, seasonality matters, and what works today might not work tomorrow. Finally, statistical inefficiency. Traditional tests require large sample sizes and long durations to reach significance. Meanwhile, you're potentially showing a worse experience to half of your users for weeks. Machine learning can solve all of these problems by making A/B testing smarter, more dynamic, and more insightful. Machine learning transforms A/B testing in 4 key ways. First, intelligent traffic allocation. Instead of static 50-50 splits, ML algorithms can dynamically allocate more traffic to better performing variants as the test progresses. This is called multi-armed bandit optimization. Second, personalized experiences. ML can determine which variant works best for which user segments in real time. A returning customer for mobile might see version A, while a new desktop user sees version B, all based on predictive models that maximize individual conversion probability. Third, causal inference. ML techniques like causal forests and meta-learners can identify not just correlation, but actual causation. They can tell you that the green button didn't just correlate with higher conversions, it actually caused them, and specifically for users in certain demographics. Finally, predictive optimization. ML models can predict test outcomes faster, recommend when to stop tests early, and even suggest what to test next based on learned patterns. Let's dive into each of these techniques. Let's start with multi-armed bandits. Imagine you're in a casino with multiple slot machines, each with unknown payout rates. The challenge is maximizing your winnings while learning which machines are best. This is exactly what A/B testing faces: exploration versus exploitation. You need to explore different variants to learn their performance, while exploiting the best ones to maximize conversions. The epsilon greedy algorithm is the simplest approach. Most of the time, 1 minus epsilon, you choose the best performing variant. But epsilon% of the time, you randomly explore other options. A more sophisticated approach is Thompson sampling, which uses Bayesian inference to balance exploration and exploitation based on uncertainty. Here's a real example: an e-commerce site testing 2 checkout buttons. Traditional A/B testing would show each button to 50% of users for 2 weeks. With Thompson sampling, the algorithm quickly identifies the better button and shifts 80% of traffic to it by day 3, while still exploring the alternative to confirm its superiority. The result? 23% fewer users see the worst experience, and you reach statistical significance 40% faster. This is the power of intelligent traffic allocation. Traditional A/B tests assume all users are the same, but they're not. Personalized A/B testing uses machine learning to determine the optimal variant for each individual user. This approach can increase conversion rates by 20 to 50% compared to one-size-fits-all testing. The process works like this. First, collect user features, demographics, behavior history, device type, time of visit. Then, train a contextual bandit model that learns which variant performs best for users with similar characteristics. Finally, serve the optimal variant to each new user based on their profile. Let's see this in action with the news website testing two homepage layouts. The ML model discovers that younger users prefer the visual layout with large images, while older users prefer the text-heavy layout with detailed headlines. Instead of choosing one winner, the site serves both, matching layout to user preference. This isn't just theory. Companies like Netflix use this approach extensively. Their recommendation algorithms don't just A/B test which movies to show, but personalize the entire testing process based on your viewing history, time of day, and device type. One of the most powerful applications of ML in A/B testing is causal inference, understanding not just correlation, but true causation. Traditional statistics can tell you that version B had higher conversions, but ML techniques can tell you exactly why and for whom. Causal forests are a breakthrough technique that combines random forests with causal inference. They can identify heterogeneous treatment effects, discovering that your new feature helps new users but hurts power users, or works great on mobile but poorly on desktop. This granular understanding is impossible with traditional A/B testing. Another powerful technique is meta-learning for causal inference. These algorithms can learn from multiple past experiments to better estimate causal effects in new tests. They understand that certain user segments consistently respond differently to UI changes, pricing tests, or content variations. The practical impact is huge. Instead of one average treatment effect, you get a detailed map of exactly which users benefit from each variant and why. This enables micro-targeting and helps you avoid harmful effects on important user segments. Machine learning doesn't just improve running tests. It can predict outcomes and optimize the entire testing process. Sequential testing algorithms use real-time data to predict final results and recommend early stopping when sufficient evidence is gathered. This can reduce test duration by 30 to 50% while maintaining statistical rigor. Bayesian optimization takes this further by learning from all past tests to suggest what to test next. Instead of random experimentation, MEL models identify the most promising areas for testing based on historical patterns, user behavior models, and business objectives. Perhaps most powerfully, synthetic control methods can estimate test impacts before running them. By creating synthetic control groups from historical data, you can predict how a new feature will perform and optimize your test design accordingly. This is like having a crystal ball for A/B testing. Let's see how this works in practice with a real case study. Uber uses ML-enhanced A/B testing for their surge pricing algorithm. Instead of testing one price multiplier against another, they use contextual bandits that consider time of day, weather, local events, and historical demand patterns to optimize pricing in real time for each geographic area. Spotify employs causal forests to test playlist recommendations. Their ML models discovered that collaborative filtering works best for discovery-oriented users, while content-based filtering is better for mood-based listeners. This nuanced understanding led to a 25% increase in playlist engagement. The implementation requires three components: data infrastructure for real-time feature collection, ML models for decision-making, and experimentation platforms that can handle dynamic allocation. Most companies start with multi-armed bandits before advancing to personalization and causal inference.
You don't have to build everything from scratch. Google Optimize offers built-in multi-armed bandits. Optimizely provides advanced statistical engines with ML-powered insights. For custom implementations, Vapil Wobit excels at contextual bandits, while EconML from Microsoft specializes in causal inference. Open source options include Causal ML from Uber, DoY for causal inference, and MABwiser for bandit algorithms. The key is starting simple. Implement basic multi-arm bandits first, then gradually add personalization and causal analysis as your team's expertise grows. Before we conclude, let's cover key best practices. First, start simple. Don't jump to complex causal inference without mastering basic bandits. Second, validate your ML models. A poorly performing model can harm your business more than traditional A/B testing. Watch out for data leakage, using future information to make past decisions. Ensure statistical rigor. ML enhancement should increase, not decrease, your confidence in results. Finally, monitor for bias. Personalization algorithms can reinforce existing inequalities if not carefully designed. We've journeyed from traditional A/B testing's limitations to ML-powered experimentation that delivers personalized, causally informed insights. By combining the rigor of statistical testing with the intelligence of machine learning, you can run more efficient experiments, serve better user experiences, and make data-driven decisions with unprecedented confidence. The future of experimentation is intelligent, adaptive, and personalized. What insights will you unlock with ML-enhanced A/B testing?